Yeah, good afternoon, everyone. So today we are going to present about the Beyond Shared Buffer. I'm Rajeev Rastogi, and I'm joined by my colleague Vaibhav Popat. We both work for Google as part of the AlloyDB database. You would have seen on our booth as well. Yeah, so let's get started. Oops. Yeah, so the agenda for today is first we are going to talk about the memory in PG. So basically, what are the kinds of memory potentially and most widely being used in PostgreSQL. Then we'll see the overview of something called dynamic shared memory. We would have heard a lot about the shared memory, but we'll get into the detail of the dynamic shared memory today. Then we'll kind of dig down further on that, and we'll get into like how do we allocate the memory and how do we access that DSM. And also there is an interesting point here that it's not a pointer, but it's mostly like offset-based DSM, so that we'll talk about that. And finally, we'll conclude with some of the applications in a sense that how Postgres has been already using that DSM. Yeah, so if you see there are like primarily, I mean, there are other kinds of memory, but we have highlighted two primary memory here. The left-hand side, which you see, is actually a shared memory, and the right-hand side is local memory. Shared memory, I'm sure most of you might be knowing. The most prominent shared memory which gets used is actually for the purpose of caching, which we also call as a buffer cache, and that's like a first level of caching for any of the operations which we do into the database. So that's a shared buffer, and it kind of, you can configure that while you are starting the server. Usually the standard and recommended way is to kind of configure 25% of the total RAM as a shared buffer. More is better, but more also can lead to the other problem. Similarly, we have another kind of memory that's called wall buffer. Wall buffer is actually to store wall-related data into the memory before that gets written to the corresponding wall files. That's again, by default, it's like 16 MB, and we pre-allocate that much of shared memory to store that wall buffer. And then finally, we have very important memory, which is a commit log, which actually stores the information about the current transaction status. So basically, whether the transaction is committed, aborted, etc. So those things get stored again into memory before they can be flushed to the disk. So if you see the common pattern across all of these memories are like they are pre-decided and pre-allocated, which means that let's say if you have to, let's say 25% of RAM as a shared buffer, as your cache is not enough, and if you need to kind of increase that, then the only way possible is that you'll have to change that configuration and restart your server. And why is that required is that shared memory is basically, it's shared across all the processes. So when I say all the processes, like, as you know, like Postgres is a process-based architecture, and like for each of the backend you connect, that spawns a new process. And since we have like single cache here, single buffer cache, all of those process or backend has to kind of access the same memory. So that's the reason it is important to have this shared memory and kind of should be accessible across all the process. So what happens that this memory gets allocated at the server start itself, and that's how all other processes can get access to that. So they will actually hold that memory pointer, and they will be able to access that. And as I said, it is like allocated by the postmaster during the start. So in case if you have to change that at the runtime, we cannot change that. Similarly is the case for wall buffer. We cannot change at runtime. And yeah, it's the same goes for the commit log. And I'm sure if you have seen the kind of shared buffer configuration parameter, you would have also kind of read that it is specifically mentioned that you need to restart. And it's not only limited to shared buffer. There are many other configuration also in Postgres, which if needs to be kind of modified, then it has to be restarted, and in most of the cases, the reason being that we cannot change the shared memory at runtime. Now, in contrast to that, we have another memory which is, let's call as a local memory, and those kind of memories are mostly per process. So when I say per process, means each process allocate their own memory, and then they can access it locally. There is no need for other backend to kind of access that. So for example, as you know, work mem, which we can configure to provide some additional memory for performing join or sorting, and these are mostly used per backend and even at per query level. Similarly, we have a temp buffer, which is also actually session level in case if you are creating any temporary table. So that's where data gets stored there into the temporary buffer, and that also kind of binded to a particular backend. And then finally, we have a like maintenance work mem, which is used for some of the auxiliary operations like vacuum and index or alter table and all. So if you see, these kind of memories these can be configured at runtime. So like work mem, you can change it even before, just before executing the query. And then the new memory will be allocated. But the thing is that this is only per process, so that's why you are able to allocate on your need basis at the runtime. So if you see, there is a like good and bad part of both. One, for shared memory, it is kind of allows you to access or kind of like multiple backend can access that memory concurrently, but it is like binded once you have started the server. Whereas local memory, you can change it whenever you need based on the kind of the requirement you are having. So yeah, so the challenge with this shared memory is like it's, as I said, it's a pre-allocated. It's a global, but pre-allocated. So now let's say if you have to get something which needs to be kind of accessed across multiple backends, but at the same time you want to allocate that dynamically. So any idea how we can do that? Yeah, so that's where this actually dynamic shared memory comes into the picture. And as we know, like Postgres kind of does not disappoint with any of the problem statement we have, and that's why like Postgres started supporting DSM, if I remember correctly, from PG version 14, if I'm not wrong. So yeah, so now let's get into the solution part of this. So as I said, it's on-demand shared memory for Postgres backends. So basically, it allocates shared memory at runtime, and the purpose remains same, that the multiple backend can access that memory. And having that kind of accessible by multiple backend helps, and that's like a key points for a database, a performant database, so that they can utilize maximum resources of the underlying machine. Yeah, so then how do we configure? It's a default, and the GUC for that is dynamic shared memory type. So it only kind of allows you to configure type of the DSM. By default, it's a POSIX, which works for most of the Linux operating system. And similarly, we have like other kind of values, sysv, mmap, or Windows for Windows machine. So yeah, so this is how you can use a DSM. So I'll just touch upon the high level of architecture. So there are three core components of the DSM. The first is DSM segments. So DSM segments are basically created, and this is also created at sort of a server start time, something similar to shared memory, but this is just a segment. It is not the actual memory here. And then the backend can pin and unpin to that DSM segment to access for their execution. And segment can be active until the point at least one of the backend is accessing that. Then again, we have a DSM control segments. So that's like a kind of maintained by the postmaster, and and still the handler of that segment gets stored into the shared memory. So as I said, that we are giving solution for shared memory, but we still use a very small fraction of the total shared memory we would have required, and that's where we use that shared memory for just storing the segment information, because that segment has to be accessed across all the backends. And these also segments kinds of help to track all the active segments and also reference count to ensure that if there are no backends accessing that dynamic shared memory, then or let's say on some crash or like abnormal shutdown, we should be able to clean up that. And then finally, we have a dynamic shared memory, dynamic shared area, which is the actual stuff which each backend uses. So basically, what it does that it allocates a reference pointer corresponding to the DSM segment, and this reference pointer is not actually a pointer. Like traditionally, we would have seen that always the memory is like a pointer, but in case of dynamic shared memory, it is not a direct pointer. It is like reference offset actually. So as I said, segments, so there will be a offset corresponding to that segment, and each of the backend can have their own offset. And that's the reason it is possible at runtime, because they are not relying on one particular memory pointer, but it is like they are attaching to one of the segment, and they have their own offset based on which they can access the memory. So yeah, as I mentioned, it's offset, and based on the offset, so basically you can just use the offset along with the DSM segment to kind of get the exact address, and which will be potentially will be accessing the same memory, and that will be across all the backends. Yeah, so this is like high level. Now we'll get more deep into this dynamic shared memory concept, and I'll hand over to Vaibhav for taking us to that depth of that.
Sure. Thanks, Rajeev, for the great high-level overview. Moving on next to what actually happens, and how as a developer we can use the DSM segments for creating extensions which have backends which need dynamic shared memory, or for any other purpose. Let's see that. So on the left, for example, we can see that, okay, first of all, DSM segment, it's nothing, it's just a 4 KB memory page that any backend can request from the OS. And the PG library provides some functions like DSM create to create the actual memory segment, and subsequently it provides functions like attach and detach, so that each backend can correspondingly attach and detach to those segments. On the right, let's talk about how actually, let's say there are two backends, right, A and B. They need some amount of memory at runtime for some coordination, right? So let's say backend process A is the one which is actually creating this memory. It uses the DSM create function to request OS for a specific amount of memory. So as part of the function argument, we pass, let's say it needs 5 KB of memory, right? What will the OS internally do is, based on the implementation type, as we saw in the last slide, the default implementation type for dynamic shared memory type is POSIX. So it will use that particular one, if that is the OS, to actually use the lower level operating system call to actually create the shared memory in RAM, right? So this memory is created of 5 KB, and then next, since this backend process has created it, what we need to do is actually map this in the virtual address space of the process, right? And in this example, as we can see on the left-hand side, let's say it gets mapped to address 0x7000, right, for this particular process. Once this is done, the next step is to actually have this DSM segment also registered in the DSM control segment that we talked about in the last slide, right? So as discussed, that when the postmaster comes up, it also creates a DSM control segment by default, so that even if, let's say, this backend gets terminated or crashed because of any other reason, the postmaster process should still be able to clean up the acquired memory, right? So that is why it is important that every DSM segment which is created, it gets registered with postmaster, and at the end it returns a handler, which is just an integer which any other backend which has to connect to the same segment can use, right? So yeah, as we saw, the backend process created the segment using DSM create, and it got a handler. Now the backend process B, it will use this handler and use the next function, which is DSM attach, to actually attach to that shared memory segment, and hence do the coordination of whatever they need. Now if we see, as in this case, let's say the handler is 1, 2, 3, 4, 5, it uses that, passes it to the DSM attach function. But the very important point to note here is the address space at which it gets mapped to backend B can be really different than backend A, and this is due to ASLR, or address space layout randomization, which is a computer security technique, so that any malicious developer doesn't know what is the actual address in the process, virtual address space of a process for a low level system call, right? And hence, whenever as part of virtual memory, if some memory gets mapped to any process, it is usually at different addresses, and they change the stack and heap locations per process so that it gets randomized. And hence, we see that this memory segment now got attached to address 0x9000 on this second backend B, right? So far so good. We have created a memory segment. The backend processor created it. It got a handler, and then it used this. Okay, one thing I forgot to mention is this handler that actually needs to be passed to backend B, right? And how do we do that? The standard process for that is to keep it in the main shared memory only, so that as part of this, we still use main shared memory, a very little bit amount just for storing some integer values, but that is needed so that other backends which have to attach to the same memory segment created get it and then use the DSM attach function to actually map to their process address spaces. So yeah, so we have discussed that it got attached, but now there are two main problems to this. First is if each backend creates their own DSM segments, they can be very much fragmented in the memory space. So it would be really difficult to figure out and manage all the segments in a very heavy traffic load application. And secondly, the main problem this has is the problem of absolute mappings. So let's say we have a struct shared stats, and we have two variables, an integer counter and a pointer. Let's say we need to create some shared memory where we have to keep the stats, right? So let's say the backend has allocated memory for this, and it got the address as 0x7000, which we can see on the right hand side, right? That is the base address at where it is mapped. Now this field pointer here, which is the void pointer, let's say that is another object which was also created in DSM, which was always also created by backend A, right? Now the problem is, since backend A has created it, the value of this pointer is in reference with backend A, and in this case, let's say it is 0x7500, right? Which is 500 bytes ahead of the base address. Now the problem is, if we have this, when backend B also connects, using the handler that it got for the same DSM segment, it would map at a different address, as we discussed in the last slide. Let's say it is at the 0x8000, which is the base address for backend B. But now, since the actual field in the struct is a pointer, and it's also hard coded to address 0x7500, the backend B doesn't really know what it means, because it actually started with address 8000, right? Because it is outside of its virtual address space. So this is a very important problem that needs to be solved whenever you create memory using DSM, and we'll come to a solution of this in the next slide. Yeah, so finally, as Rajeev said, we have a solution for every problem. As part of the DSM, because of this problem of having lot of fragments, and also having this problem of when you have pointers in a DSM memory struct, it cannot be referenced by another process. So PG also provides a wrapper over the DSM library called as DSA, which is dynamic shared areas. These are basically just an abstraction over the raw DSM segments, and what it uses is it uses the DSA pointer. So the DSA pointer is just a fancy name for an integer handler, but what it deals with is always integer handlers instead of raw addresses, so that they can be actually be referenced by all the backends which attach to the DSM segments. We'll come to a live example of this in the next slide, where we can see how the previous problem was actually solved. But before that, if we see on the right hand side, we can see that okay, the DSA dynamic shared area is just a wrapper over few segments. What happens is, let's say a backend has to, if we go back to the previous example, right, where backend A used the DSM create function to actually create the segment. Now instead of that, what it would do, it would use the DSA create function, which is what internally it would actually allocate one DSM segment and provide a handler for the DSA area. Once that handler is there, any other process which needs to map to the same DSA area, it would use the next function, which is the DSA get handle, where you pass the handler and you get the actual address, which is local to that second backend process. And accordingly, next it can use the DSA attach function to actually attach to it. So in short, what has happened is, we created a DSA area, we got a handler to it, and another backend actually used that handler to attach to it, right? And now on the right hand side, we see two functions which are DSA allocate, which actually does the memory allocation. So here we pass the size which is needed for the memory struct. And the beauty of this dynamic shared area is that as and when more memory is needed, you don't have to call or you don't have to care about what is the number of DSM segments which are getting mapped internally. It auto expands, and based on the size needed, it will actually fill probably the complete virtual address space as well if it allows, right? But the thing is, we now have a wrapper over the managing the low-level DSM segments so that all the backends can actually map to the same virtual address space. Okay, now coming to the next slide where we'll actually see that how this problem is solved. So the simple solution to this is, if we go back to the previous slide where we had a void pointer, instead of that, now we'll have a DSA pointer, which is actually an offset. So what we need to do is, in case of backend A, where we initially stored the address as 7,500, instead of that, we will store the offset value as 500, which is just 500 delta from the base offset of 7,000, right? So now what will happen is, whenever any other backend, let's say in this case backend B attached at address 8,000, it can use the offset to actually calculate the delta for the next field here, which is the offset, and that is how it can actually translate where the next memory in location is. So just to give a TLDR, the simple thing that we have to keep in mind whenever we use DSM for memory allocation is that if you create a struct in dynamic shared memory, if it cannot have a pointer to any other struct in dynamic shared memory, right? It always has to be offsets. There are exceptions. Let's say you have a circular buffer and you just have a string of let's say query length or something. If the same thing is completely in the struct, then it is not an issue because any other backend will use it. But whenever you have a pointer to any other thing, you always need to keep an offset so that the next backend which gets attached at any different address can also seamlessly calculate it with the offset and hence get the actual memory location instead of having a memory corruption. So yeah, I think that was all we had, and yeah, just wanted to share some applications of DSM and DSA in OSS. So I believe this feature was mostly created for parallel query execution, where it was thought that with very high workloads where we have a single leader process and it creates multiple child processes to communicate, it is difficult for them to get a runtime memory so that they can coordinate their actions as part of the query processing. And this feature, I mean, DSM feature is the main use of this feature is as part of the parallel query execution and parallel indexing. And secondly, we can also use this as part of inter-process communication between different background processes, as well as some custom extensions where you need all of this new process which you create or to actually coordinate memory among themselves. And yeah, that's all we had. We have some references for DSM, DSA.